So we're heading into the home stretch. This is the 10th video, and it's about regression analysis. Regression analysis is something you're going to see quite often in the biomedical literature, and it can be somewhat mystifying. So what would you say it is? Um, some days, mostly every day. Yeah, this is how a lot of people treat it, and this is what it becomes when you don't understand what it means. So let's go back to the weighting and burnout study from the previous video. So you've got your data and you want to put it in a 2x2 table. There's the magical 2x2 table. And the authors have noted that there are wait time targets that are assigned administratively based on the ESI triage level. So there we are. So you can organize the patients in, did they exceed the waiting time target or were they underneath the waiting time target? All right, half the 2x2 table is done. But how do you categorize burnout? Just if you're at all familiar with burnout, there's a Maslow inventory for burnout, and it's a numerical scale from 1 to like 35, something like that. So is it like the middle number? Is it everybody from what is it? 16 and below gets or 18 and below gets low burnout, and everybody above, it's difficult to say. So it's greater than or less than the middle score, less than the median score, perhaps. The random percentile, whichever cutoff you want. Can you make multiple categories? Little burnout, a lot of burnout, somewhere in the middle. Should you just slice and dice until you get a p-value? And guess what? That's what the authors did instead of using regression analysis. So, but here we go. The, shocker, I know. The 2x2 table is not everything in epidemiology and biostatistics. So regression is when an input is linear, the input being the purported exposure phenomenon, and like if you're looking at heart rate or ED volume, dollars spent, if you think that it's going to be hard to generate a cutoff somewhere logically based on clinical phenomenon, regression is probably the answer. So a regression analysis is a fancy schmancy term for an XY graph from algebra. So you plot the inputs, which are usually reserved for the purported cause of a phenomenon, and you plot the outcomes or the purported effect on the y-axis. And if those dots seem to form a line, you've got a regression analysis. And you can see up here y equals 8.1707x minus 699.54. That is your classic algebraic line formula. Y equals mx plus b. So it's the previous example, it's 8.1. What that means is for each additional 1 degree Fahrenheit, the heart rate on average raises by 8.1 beats per minute. So that's pretty close to the old yarn of 10 beats per minute for each degree Fahrenheit. All right, RSquared. This measures how well all the points cluster around the line that the researchers, imagined essentially. So 0 means there's no relationship whatsoever, to 1 means that all the dots form a perfectly straight line. And in this case, an R-squared of 0.1 means that the factors chosen for the analysis account for about 10% of the effects shown. So that kind of makes sense. Heart rate is caused by a lot of things, and in a febrile patient, the height of the fever accounts for about 10% of the effect shown. Here's heart rate and pain scale. And you can see that the line is actually not really all that helpful. I made a line, but logically there really isn't a line. And you can see that pain scale only accounts for 2% of the variability seen. And in fact, if you look at the M, it's negative 0.8, which means that for each 1 unit that the pain scale increases, the heart rate actually decreases by 0.8452 on average. And there's probably 2 reasons for that. First of all, if you look at the extreme left of the graph, that's where the pain scale is 0. You've got some very high heart rates there. That's probably things like AFib and SVT, which people can be very tachycardic, but will have 0 pain with that. Also, I think the other factor dragging this down is that I think we've all experienced patients who report their pain scale as 10, but we're secretly very suspicious if they are attempting to engender a sense of immediacy that they are worried that we would otherwise not take them seriously without them reporting a pain scale of 10. I think that's a very polite way I've found of phrasing that. So multiple regression, we're going to move on. Harder to depict, but basically imagine the same graph, but now in 3 dimensions, 4 dimensions, 5 dimensions. Our brains can't handle that because, we're trying to piggyback on a visual front, which our brains are very good at when it's 2 dimensions, maybe 3 dimensions. But once you get into more than 3 dimensions, our brains can't handle that. But guess what? Computers can handle that. And it allows you to see basically what happens when you put multiple inputs on one outcome. Each input will have its own coefficient and its own individual p-value, but the whole set will have a single R-squared. And you can have items which aren't truly linear, like EMS arrival, plugged in. So basically, if a patient arrives by EMS, you code their EMS arrival as 1. And if they self-present, and then you code it as 0. So the EMS-ness will increase the outcome of the coefficient reported. Logistic regression is another type of regression. And it's similar in construction, except the outcome isn't a scale of values, but instead it's a yes-no thing, like mortality. You can't be 99% dead, outside of Hollywood. The equation will still report coefficients in an R-squared, but the coefficients are odds ratios. So it's the odds of the outcome occurring given that a particular input was present. And there's one more trick regression brings to the table. You can use multiple regression to adjust for the effect of confounding variables. A lot of time when you see a paper report, we use regression to adjust for confounding variables. This is precisely what they're doing. They're canceling out the effect that those confounders have on the input that they're examining. So if you want to see specifically what the effect of aspirin has on heart disease, but you want to cancel out gender, age, smoking, you can use that. And if the causes of an outcome may be multifactorial, you can use multiple regression to throw it all into the mix. So here is from the waiting burnout study. They used logistic regression, and they could have used linear regression. They should have used linear regression, but that's neither here nor there. So what they did is, you can see that if your burnout score was greater than 35, then the adjusted odds ratio of missing your administrative waiting time target was 1.53. And if it was greater than 75, if your age was greater than 75, if the patient's age was greater than 75, it increased it by 1.48. Obviously, if the daily occupancy was, greater than the maximum, then that increased it. That's pretty obvious. So what they're doing essentially is, by throwing all these factors into the mix, they are adjusting for them. So they've been able to adjust for age, adjust for the occupancy, adjust for the ESI triage level, adjust for trauma patients, adjust for, afternoon and evening visits between noon and midnight. They probably adjusted for all the days of the week. Sunday was probably the only one that was statistically significant, and like our hospital, their Sundays weren't very busy, which meant that if you showed up on a Sunday, your odds of missing your administrative wait target was reduced by 0.62, the odds ratio. So all that makes a lot of sense. Well, yeah, I forgot to clickety click it. All right, I'm going to leave this stuff up here for a bit. So what this is saying is, when we say the adjusted odds ratio for burnout score greater than 35 was 1.53, then that means age doesn't factor into it. Daily occupancy, ESI level, whether it was a trauma patient, what time and what day the patients came in. None of that plays into it. Now, of course, this doesn't take care of hidden confounders, especially if you don't throw them into the model, but all right. Now, when you do the multiple regression, you don't have to actually report all the coefficients that you derive. All you have to do is we adjusted for it. But if they're not the focus of your study, especially if they're known, well-established confounding variables, there's plenty of research. You don't need to reinvent that wheel. All you have to do is report the thing that you are specifically researching. So to wrap it up, regression is a great way to retain linear inputs without losing data by forced categorization. You can include multiple inputs simultaneously as they factor into an outcome. You can remove the effects of confounders from a factor, and remember what to look for. The coefficient is the magnitude of the effect. The R-squared is how well the line fits, and the p-value is the p-value. All right. Now remember, if you have any questions and are taking the course, don't hesitate to email me. If you're not taking the course, don't hesitate to drop a comment down below. And if you are taking the course for credit, don't forget to take the quiz, which is in the show notes.